Hi guys, BuildZoid here, and today we're going to be doing a PCB breakdown of the X570 Phantom Gaming ITX Thunderbolt 3. And before we get into the PCB breakdown itself, and I just dropped my stylus, before we get into that, I just want to point out something about, Asrock's advertising of this motherboard. So here, they're like, oh yeah, this board totally supports 4533 megahertz. And then you look at the QVL, and where's the 4533? I don't see a 4533 on this list. I see a 4266, and that's already like there's one 4266. Now, this could be well, first of all, this just shouldn't be up here as far as I'm concerned. That's just lying because they never tested that, or at least well, it's not that they never tested that. The issue is that basically if you bought a memory kit that runs at like 4400 megahertz, you stuck it in this motherboard and then it didn't post, and you told Asrock that you're having issues with it, they'll just basically go to the QVL, go like, oh yeah, we don't support your memory kit because this QVL doesn't support anything rated above 4266. So if you have issues with high memory speeds on this motherboard, they're just going to ignore you because you've technically not bought something that's on the QVL. So anyway, so not really a fan of that. The other thing that I see that is concerning to me with this QVL is that it does end at like 4266, which is pretty damn low. And then, all of the other kits are just 3600 megahertz. Like, this QVL is actually really kind of crap, as far as I'm concerned. For 16 gigs DIMMs, it tops out at 3200 megahertz. For 8 gig DIMMs, it tops out at 4266 for one kit. Now, it could be that, there's some kind of BIOS issues. It could be that they didn't test enough memory kits, so the QVL is just kind of it's not complete. But the thing is, there's other concerns I have with this motherboard where it's like, I don't think it necessarily is the QVL or the BIOS that's screwing this board over, but the actual board itself. So let's take a look, shall we? Now, the thing is there's a lot of other things that I do like about this board, like the VRM is really impressive. And yeah, but the thing about the memory is, well, this. Okay, so actually, this is a bulk capacitor for VDDR, so that's where it's supposed to be. Okay, we don't need to get rid of that. But the thing is I've said it in past videos, and I'll say it again. It doesn't matter how you power your, for the most part, it doesn't matter how you power your DDR4. What matters is what happens between the CPU socket and the DIMM slots themselves. So basically, what's important is what you have in this area of the motherboard. And what we can see here is there's a freaking crystal oscillator sitting above the memory traces, which is that is that's just a noise hazard if ever I saw one. There's a BIOS chip sitting over the memory area. There's a freaking PWM fan header sitting in the memory area. There's a little buck converter sitting here. There's a whole bunch of ICs that as far as I'm concerned, have nothing, no business being located in this area whatsoever. And it's just okay, so, that QVL, really unimpressive. Honestly, kind of disappointing considering this is a 1 DIMM per channel board, but this is a board where it really Asrock basically ran out of space to the extent that I would not be surprised if this motherboard, I don't have this board. I've not tested it. But if I did have this board and I was testing it, one of the things I would focus on is how good is it with memory overclocking? Because, you see a lot of other board vendors go to ridiculous lengths to basically MSI basically has the visually indicated keep out zones for the memory section. And EVGA also does that. And then on Gigabyte boards, you don't have a big visual indicator that, this is the memory area. There's not going to be non-memory things here, but you still don't find, random ICs just kind of sitting in between the DIMM slots and the CPU socket, because that just makes your job more difficult when it comes to ensuring signal integrity on the DDR4 traces. And then there's Asrock where they're like, well, we've run out of space everywhere else on the board, which is fair. There literally is not enough space on this board. But yeah, the downside to that is this board, if this has terrible memory overclocking, I'm going to say it's because of all of this stuff right here, and maybe that fan header as well. So Yeah, and I just wanted to point that out is just like, because a lot of the time with ITX boards, especially if like the actual effort, because the thing is with ITX boards, you're stuck on 1 DIMM per channel, mostly because you physically can't fit 4 DIMMs onto these. But often but the side effect of that in for a lot of board vendors is that, hey, it kind of gives them an excuse to make a motherboard that's ridiculously good at memory overclocking. So, I'm thinking like MSI's Z390 ITX board where it's just like, well, it's 2 DIMMs and it's absolutely insane. When it comes to just raw memory frequency, it's great. And then you look at, and then Gigabyte, their ITX boards tend to be better than their full-size boards, at least for like 1 DIMM per like raw frequency attempts and that kind of thing. And then there's Asrock, where honestly, like the Z390 ITX, I've think is pretty decent. I didn't really notice. I didn't I still haven't finished testing it, so that kind of sucks. Yeah, this board, this memory section is very concerning as far as I'm concerned. As far as I'm concerned, this is concerning. Like none of this should be in this area. And I get that there's not enough space on the board, but the downside is that, well, the thing is I guess you can kind of go with, as long as the motherboard runs, at least 3800 megahertz, then you're fine, because that's generally where you're going to top out due to the Infinity fabric. But I don't know, like, is it even capable of doing that, considering that the QVL ends up for 3600 with the exception of like 1 memory kit, right? So yeah, the memory section here is kind of concerning to say the least, and is definitely something I'd really like to see tested in depth from anybody who has the board. I might look into getting the board. I don't really, like, the thing is, I don't want to say that I'll definitely test this thing, because right now I already have way too many boards to test, and way too much stuff to test, and not enough time to do all of it. So it's just like, the last thing I want to do is like, yeah, I'm going to test like 10 boards and then realize, there's just no way I'm actually ever doing all 10 of them. So yeah, but this, like, this is still a really interesting board. It's just like the memory section is just like that needs like, I want to see tests of that, like a lot of them, because this is like, yeah, like most of the time you see motherboard vendors just, bending over backwards to keep the memory section free of non-memory things, and then there's Asrock where it's just like, we ran out of space. put the, like, I'm pretty sure that's the oscillator for the BCLK of the CPU. Just put that right between the memory slots and the CPU, right? Well, who cares? It's going to be fine. Could also be that one, I guess. But yeah, so that's kind of that. Anyway, for powering the memory section, since we're on memory, we might as well rearrange my video layout a bit. That chip right there is the actual buck converter for the memory. So that's that right there is the VDDR rail, and that chip over there is a Monolithic Power Systems MPQ. I think it's an MPQ. My notes are stupid because my notes for some reason say MPS, which is like Monolithic Power Systems. Do they? I think they actually do brand some of their chips MPS, but this one I know for a fact is not MPS. I'm pretty sure it's MPQ. So anyway, for some reason my notes don't have that, because they just have the actual like model number, which is 8633B, and that's a 20 amp buck converter, which is more than enough for powering a DDR rail. And keep the B is important because there's a 8633A, and that's like a 12 amp buck converter. So yeah, the B is actually important. The 12 amp one would be like barely within, requirements for DDR power, but a 20 amp is perfectly fine. So yeah, and that's actually a pretty impressive like memory VRM, but because a lot of the time, because like this is a pretty, like relatively high switching frequency controller, and it's pretty fancy compared to what you see from like, say, like a lot of other board vendors. They'll just go with like a pretty basic, discrete component buck converter and run it at relatively low switching frequency. So, but I guess Asrock's basically using this because they just don't have enough space to have a bunch of capacitors, because it's like you have that tantalum, and that's the entire bulk filter for the entire VDDR rail. So Yeah, very, very space constrained board. Anyway, like in terms of power delivery, it's fine. The actual memory itself looks, the rest of the memory system looks kind of concerning. It looks pretty concerning. Anyway, so let's move on to the much more, well, arguably more important, but definitely much more substantial vCore and SoC VRMs, which are actually split up like this. So we have a vCore that is an 8-phase. And then we have an SoC, which is a +2 phase. And the controller here is an ISL 69147 running in a 4+2 × 2 +2 configuration. The ×2 is achieved through a bunch of doublers on the back of the board, because otherwise it wouldn't be ×2. Otherwise it would just be 4 + 2, because that's the control scheme, not the, because you can put more MOSFETs into a single phase if you feel like it. It doesn't give you more phases, right? You can also put more power stages onto the same PWM signal, doesn't give you more phases. So the doubler used is an ISL 6617 from Intersil as well. And those are, of course, on the back of the board, because you can't see them on the front. And so that's these chips right here. What's kind of interesting about the ISL 6617s is that, unlike a lot of, they have the most advanced current balancing system built directly into a doubler. So these chips will actually monitor the current going through each of the phases, and they will do actual PWM pulse extensions to basically to get current balance between the two phases. Now, at least if they're configured to do that, there's a bunch of setting options for them as well. For comparison, a lot of other doublers, they'll do things like phase skipping, or if you look at something like a 3599, that doesn't do any balancing of its own at all. But with international rectifier voltage regulators, the actual controller has configuration options to see, to work around, to do current balancing through the doubler anyway. So that's kind of that. So, we've got that for the control scheme. So this is about as true an 8-phase as you could get. Now, the downside to running the doublers is actually that you do add some delay to your PWM signals. So any kind of advanced PWM manipulations that the controller can do to try improve transient response, they're less effective because they're delayed by a couple nanoseconds. Now, the thing is, the control loop of the controller itself is not the only thing you have to worry, not the only thing that affects your transient response. Your capacitor selection, your inductor, how low, the inductance of the inductors affects it, the capacitors on the output affect it. So, well, actually, that's kind of it. That's the two main things. You can have more capacitance and faster capacitors, and you can have lower inductance inductors or higher inductance inductors, depending on what you're going for. And that'll also affect your transient response. So it's really you can't say, oh, this VRM is using doublers, therefore it will have a worse transient response than a VRM that isn't using doublers, because this could very easily just, make up the difference on just the output filtering alone, where it's just the output filter on this can soak up transients much more easily than the output filter on another board. And for certain types of transients, that's actually just better. If your output filter is just better, that's generally better, because that thing works always and all of the time, whereas with the CPU, you can sometimes get transients where they're just very, very, very short. And so they're just faster than what the control loop can do, even if you, faster than what the control loop can easily deal with, even if you eliminate the doublers. So in that case, it's just okay, well, you're just going to need, at some point, you just need better capacitors, right? So, yeah. So I'm not going to, basically, it's a topic that you can, you can't go and look at a VRM and say, hey, this has better transient response than that. This might have better, might be, well, honestly, I don't know, because this uses such wildly different, the capacitors on this are so much better than what you get on normal ATX boards, just because it's an ITX. It's unintended side effect of having a small form factor motherboard. Better capacitors, because you can't fit the cheap big ones. But the thing is just so you have a completely different style of output filter compared to ATX boards. And then you have a very different control scheme compared to a lot of ATX boards. And it's just like, well, at that point, it's impossible to say if this will be better or worse than, motherboards from like Asus or Gigabyte or anyone like that. So, because it's just like there's too many variables that are different between the boards. So you can't say, okay, well, you'd need to measure it. So anyway, let's take a look at something that isn't too testing, like doesn't require, isn't as is easier to get right off of just data sheets instead of worrying about like the actual implementation. And that is the efficiency of the power stages. So Asrock here is using a bunch of ISL 99227B 60 amp smart power stages from Intersil. And I love these things because they're really, really, like, they're ridiculously efficient. They're extremely expensive, and they're freaking awesome. So, they are a smart power stage. Smart power stages basically have a few advantages that are like insane efficiency compared to a 60 amp, right? Previous generation 60 amp power stages. These are just better. They integrate better, more accurate current monitoring, more accurate temperature, not more accurate temperature monitoring. Temperature monitoring doesn't, there's not really been some great advancement in doing temperature monitoring of power stages, so no. But the current monitoring did get an upgrade. Overcurrent protection, over temperature protection, and I think even some short circuit, other advanced protections are there's definitely other advanced protections. I've just forgotten what they are because I don't find them that interesting. Anyway, so these are freaking awesome power stages, and they're insanely efficient. And this motherboard, as a result, actually gets a really high VRM efficiency. So outputting 1.2 volts at 500 kilohertz switching frequency with, and that's not a very good, that didn't make the K any better, did it? That K is terrible. There, that's a K. 500 kilohertz switching frequency and 5 volts drive, which that's the only voltage you would actually run these on, just straight 5 volts. This VRM would be able to push 100 amps while producing only 8 watts of heat on the power stages. So, insane efficiency. Now, this is actually in line with the efficiency you could get out of a 70 amp smart power stage from, say, Infineon. The thing is, the only motherboards that use those crazy high-end 70 amp smart power stages from Infineon, there's very few of those boards, and they don't actually no, there's going to be the Impact from Asus. So the Impact's probably going to end up with the same efficiency figures across the load range, because these are there's barely a difference between the 70s and the 60s. The reason why these are the main reason these are rated for 60 amps and not 70 is because they're in a smaller package size, so it's actually harder to cool these, even though they do have the exposed metal tab here, which is hooked directly into the switch node of the phase and is meant to reduce the thermal resistance of the actual component so that it's easier to cool the power stages. And that's also a really expensive add-on. That actually is probably the most expensive part of this entire chip, is the fact that metal tab right there, because if you look at the price differences between some other power stages where they come with say a 3555 versus a 3575, the price difference between those two is insane. And the only addition is that metal tab. That's the only change between the two. So yeah, this is expensive because it makes the packaging process much more difficult. Much more complex. It's done by machines. So, machines don't really do difficulty, but they do complexity. Anyway, so 100 amps output, 8 watts. This board should basically have no issues handling any kind of 8-core overclocking. You go up to 150 amps output, it's going to produce about 12 watts of heat. No problem with any kind of 12-core overclocking. And then 200 amps of current output, you're going to be looking at about 18 watts of heat. And I forgot to put the about in front of those. 18 watts of heat. So even a 16 core, this board should really not have any major issues, especially considering that, Asrock's gone ahead and they actually have the VRM split up properly. So you're not going to have one of the, basically they have 2 V-core phases up here and 6 V-core phases down here. So it reduces the thermal density of the V-core VRM. And this is a really good way to get better thermals on any VRM, really. Just don't put all of your power stages right next to each other. So basically, if this board was pushing, say, it's a nice 8, well, let's just round that up to 20, okay, for my convenience. So if this was pushing 20, like producing 20 watts of heat, which would be maybe like 220, 230 amps, I want to say, maybe 240 amps, something like that. You'd have basically 15 watts of heat right here and 5 watts of heat right here. 15 watts is not that hard to deal with. And 5 watts is also not very hard to deal with. 20, on the other hand, actually if you have 20 watts all jammed together, that's actually hard to deal with. You start needing a significantly more substantial heatsink. So, yeah, I'm a big fan of the fact that, like, Asrock has the VRM split up like this because it does make cooling it much, much easier. So, yeah, and then, the insane efficiency just is great. So if we go into theoretical current outputs, like 300 amps, you'd be looking at about 35 watts of heat. 400 amps, you'd be looking at about 54 watts of heat. And 480 amps, which is the absolute limit of what this VRM can produce, right? Eight phases times 60 amp power stages in each, 480 amps. At that point, this VRM would produce about 86 watts of heat because, again, that 60 amp power rating, that 60 amp rating on these power stages is assuming that you have one power stage with a very large heatsink for it. It's not meant for, it's not a specification meant for like use in a multi-phase configuration like we have here. So yeah, basically in the practical output current range, like the 100 to 200 amp range, this VRM is absolutely great. If you like wanted to do LN2 overclocking there, this really wouldn't work that well. But I don't really see a reason why anybody would want to do LN2 overclocking on a board like this, right? Like, there's better options for that aren't ITX. So, yeah. Anyway, what else did I want to talk about? Well, the SoC VRM is just more 60 amp smart power stages, so that's just massive overkill right here. And I guess at this point, let's take a look at the heat sinks that that have to deal with all of this heat output from the VRM. So this is the little heatsink for the SoC and 2 phases of vCore. It doesn't really have much in the way of surface area, but it can probably deal with 6 or 7 watts of heat. At least I'd assume so. So yeah, at least deal with. The VRM should be able to, the VRM might hit 100 degrees, which is fine for VRMs. And then this heatsink might be able to actually dissipate 5 watts of heat or something like that. 5 to 7 watts of heat or whatever it is that it needs to deal with. So, that's really only a concern if you're on a 16 core is this heatsink. And the 16 core currently isn't even available. And depending on your case airflow, this heatsink could actually dissipate a lot more heat than that because airflow is totally overpowered. If you literally, a gentle breeze is so much of a difference to cooling capacity, because the thing is, the airflow due to we all know hot air rises, right? But hot air rises extremely slowly. So even a gentle breeze will make a massive difference to how much heat you can actually dissipate with even a heatsink like this, right? Where it barely has any surface area to start with. This is still a lot more surface area than the MOSFETs though, right? Keep in mind that the MOSFET has a contact patch to the heatsink that's down here. So if you literally just go, okay, if you consider, well, actually, this goes up against the choke. There's not going to be any airflow down here. But basically, from this point to this point, you have usable surface area, which is significantly more than what a, bare MOSFET would have. So, it doesn't have any real fins to it, but it is just kind of one big fin of itself. And it could do a decent job. I don't see this necessarily, it only has to deal with single digit wattages, so it should be able to deal with that. Then for the vCore VRM proper and the chipset, we get this right here. So the chipset fan will either help cool your VRM or your chipset, depending on whichever one is running hottest. And I'm actually a huge fan of how Asrock turned the entire I/O cover into the VRM heatsink. I don't get why we don't see more boards with this. For some reason, it seems to be that everybody decided, what's better than having a giant slab of metal as an I/O cover that could act as the heatsink for the VRM, having a small small aluminum heatsink for the VRM, and then covering that up with a big plastic I/O cover. Like, just make the whole I/O cover into a heatsink, and then you both get your I/O cover and better VRM cooling. Because yeah, sure, this doesn't have any any obvious fins, but it has a ton of surface area. Like, it's like the whole thing's a heatsink now. Right? It's one giant fin, effectively, with some funky bends to it. So, yeah, I'm a big fan of how Asrock decided to deal with the VRM cooling. I can't really, like, this board should run, like, the VRM on this board should actually run really, really cool. So, yeah, I'm a big fan of how Asrock decided to deal with all of that. Yeah, so the heatsinks on this board, definitely a fan of those. And let's still stick with the power delivery stuff. So, heatsinks, MOSFETs, great. All of that's great. For the capacitors, well, for the big bulk ones, which I think we only have these right here. Is that really it? Is that, yeah, that's the, oh no, there's 2 more through-hole capacitors, but that's the audio section, so I don't pay attention to that because I'm not interested in audio that much, or at least not onboard audio. Anyway, so for the big through-hole capacitors, we have a bunch of Nichicon FP12K series capacitors, which this is like a special order part that Asrock puts an order in for because you can't buy an FP12K. That's not like Nichicon, like if you just go buy, Nichicon capacitors off like DigiKey or something, they top out at, I think, 5 or 10K. You can't buy a 12K spec. That's like a special order that Asrock makes. Anyway, so those are aluminum polymers. They are through-hole, so they'll last forever, basically, because that 12K, that's 12,000 hours at 105 degrees. So yeah, and that's just a thing that Asrock likes to do because that's just what they decided to do with their capacitors. So that's for the 16. Those are 16 volts because they're sitting on the plus 12 volts rail. So anyway, on the output side though, we have SMD aluminum polymer, or I assume aluminum polymers. The thing is, this package, a lot of people assume that's tantalums, but actually, Panasonic has this. This is like, if this was, I'm not sure that these are Panasonic, but Panasonic does their tantalums in this package, and you can tell they're tantalums because they have like this type of marking. But they do their aluminum polymers in this package for SMD. So yeah, we have SMD, what I assume are aluminum polymers. And the thing about these is that they're way better than through-hole aluminum polymers. They're also way more expensive, like 4 or 5 times more expensive than your typical through-hole aluminum polymer. But the thing is, like, they have lower ESR, they have lower ESL, and unfortunately, they don't make them. They're kind of hard to get in really high endurance ratings. But the thing is like, if your VRM just doesn't run really hot, you don't need a high temperature, high endurance rating, right? Because you're freaking never gonna hit a high temperature. And in that case, these are just superior because you have the lower ESR, you have the lower ESL. They are just much better at doing things like soaking up fast transients, and filtering out VR, like the switching noise from the VRM, switching noise from the CPU. Just these are just better. Okay, if all you care about is the level, is reducing transients and that kind of thing, these are just better than your through-hole capacitors. That's just a fact. They're also way more expensive. Other than that, kind of an interesting thing that I think I've only noticed Asrock doing this is these huge multi-layer ceramics. Now, I actually started looking into these recently because, I big multi-layer ceramic capacitors. I'm interested, right? Are they good? Are they bad? Turns out these are actually not really that special. So last time I checked these on an Asrock board, they were 68 microfarad. I assume they still are. The thing is, if you actually look at the sort of the impedance and the so again, the ESR and the ESL of these, it's actually not that different from your full-size SMDs. Like, these and these, in terms of the frequencies at which they're effective, are pretty much the same. Which really surprised me because I figured these would actually work better in higher frequencies, but no, apparently they're actually not really that great at that. So I assume the main reason Asrock is using them is just like they ran out of space for the, larger SMD polymers. I guess they could have squeezed one up here, but anyway, for high frequency filtering, we obviously have the multi-layer ceramics right behind the CPU socket. Incidentally, a good chunk of these little ones are actually on V-Core. I checked that on one of my other X570 boards, because initially, because the thing is, a lot of the little multi-layer ceramic, there's a bunch of multi-layer ceramics that get used for the PCIe signaling lines, that I've noticed that they'd be hanging out usually around somewhere in this area of a lot of boards. But yeah, here, like, a good chunk of them is also, like, and I think still some of these are on PCIe. I've not actually, like, I've not checked which ones are for what. But I did find a couple that are definitely for V-Core. So that's actually a pretty big difference compared to, like, old AM4 boards like X470 or X470, B450, X370, because you wouldn't really see these really small multi-layer ceramics. You'd basically just see what you have down the center right here, and the smaller ones are obviously for just higher switching frequency noise. So it's kind of interesting that, you know, the X570 boards basically have like more high frequency filtering right behind the CPU socket. Also, we have more of that over here for V-Core, right? You can see how that's connected, and over here. And then, of course, we just have more SMD aluminum polymers. They also have some tantalums on the plus 12 volts right there. So these are mostly a space constraint thing. But again, these have advantages over their through-hole counterparts when it comes to just, you know, ESR and ESL. Just the package is just superior. So, yeah. This is like, as far as the actual, like, V-Core and SOC VRMs go on this board, I really, really like it. I would not be surprised if this board, you know, it, like, basic, like, I'd have high expectations for this board if I put it under an oscilloscope. Like, I would expect it to do pretty damn well just because of the capacitor selection that you're looking at on the output filtering, which the stuff they have right behind the socket, that's actually the same across most boards, but the bulk capacitors here are just better than what you normally get on a motherboard in this price range, because this board is only $239 on Newegg. So yeah, it's just, like, in that price range, honestly, I would not be surprised if this VRM just kind of blew everything away. Because I've already tested a different ITX board, and that's actually, like, that's what we ran into with Gigabyte's ITX board, where it was just like, I looked at it, and I was like, well, it's a 6-phase, and it's got a bunch of SMD aluminum polymers. I would be very surprised if it wasn't better than all of the ATX boards in the same price range. And turns out I was right. Like, that ITX board just kind of blows everything else out of the water in that price category. And so this board, I would assume, do the same thing, because it basically has the same main, you know, benefit that you see on the Gigabyte's ITX board, where it's just like SMD aluminum polymers are kind of overpowered. So yeah. VRM wise, I really like this thing. The memory section, though, concerning to say the least. And the VRM on this is actually more powerful than what you get on the Gigabyte ITX board. So thermally, this one should do better. And also, Asrock has more substantial heat sinks for their VRM on the ITX board as well. So yeah, except the thing is obviously with Ryzen 3rd gen, you know, the priority isn't so much what you can do with your most people are probably just going to run their CPUs at stock, and so the VRM really doesn't matter that much. But what a lot of people will overclock is the actual memory, and that's where I think this board actually probably has a massive disadvantage over a lot of the other boards, because this memory section just looks like a mess, because there's too much stuff in it. Like, this should just be this should be empty. There should be like that maybe like one or maybe a second one of these capacitors, and that should be it. Like, there shouldn't be anything else in between the DIMM slots and the CPU socket. So anyway, but VRM wise, Asrock, you know, manages to impress again, and this is actually an upgrade over what they had on the Z390 Phantom Gaming ITX. So I'm really, like, Asrock kind of knows what they're doing with ITX boards, I'd say, for the most part, in some sections. Like, they make some interesting ITX boards, right? Very interesting ITX boards. And at, like, decent prices as well. Because the Gigabyte board is $220, I want to say. So, you know, they're like $219. So basically $20 cheaper. And yeah, Asrock managed to squeeze in a significantly better VRM. But the thing where Asrock kind of loses out, as far as I'm concerned, is the rear I/O. So we have a combined PS/2 port, 2 USB ports, Wi-Fi 6, which you get, like, think the ITX from Gigabyte gives you that as well. And then instead of more USB ports, Asrock decided they're going to give you a Thunderbolt 3 port. So this is, a motherboard that you're going to need a dongle for to get a decent number of USB ports from. So that kind of sucks as far as I'm concerned. Like, yes, well, for a lot of people, like, there might be some people who explicitly want Thunderbolt 3, but for everybody else, I feel like this is just, for like annoying because now you need to get Thunderbolt 3 to USB dongles, which I like, I'd prefer just having more USB ports, and I think most people would agree with me on that. And the thing is, they actually have a lot of empty space above that. It's just like empty space above the Thunderbolt 3. There's not any space on the board to put USB ports, right? Like that's a USB port header. Like, yeah, that's not gonna fit right there. But the thing is just like, yeah. So if you like Thunderbolt 3, great. If you don't like Thunderbolt 3, that actually kind of sucks. You got more USB ports over here, 1 gig Intel, which is also like that's the same as what you get on the Gigabyte ITX board, so no advantage there. And we do get a clear CMOS on the rear I/O, but which I don't think, yeah, the Gigabyte ITX board doesn't get a clear CMOS, but it does get BIOS flashback. And this board doesn't have BIOS flashback, and it is a single BIOS board. So, like, if you break this, like, if you screw up a BIOS flash on this board, you're going to have a bad day. So, yeah, that's kind of this board has its strengths and it has its weaknesses, especially in the rear I/O section. It's a bit more expensive. VRM-wise, you get an upgrade. Memory-wise, it looks like a downgrade to me, at least. Obviously, it's impossible to just look at a motherboard and say for sure that it's going to be bad at memory overclocking. But generally speaking, when you have, like, this, memory is hard to lay out, even when you have all the space in the world to do it. Asrock here have... it's an ITX board. There's already not a lot of space. And then they're like, oh yeah, we're just going to cram a bunch of extra ICs into the memory section. So, already a difficult task, and they're just making it worse. So, yeah, it's an interesting board. I wouldn't, rush out and buy it because, there's some compromises to it. And some advantages, like you do get the Thunderbolt 3, which I think is really cool for some people, and for everybody else, you just want more USB ports, which this doesn't really offer. You get a better VRM, which also, the other compromise that they made is to get this larger VRM on here, Asrock did opt to use the LGA 1150 spacing. So 1155, 1150, 1151, all of these actually have the same hole spacing. So yeah, Asrock's using the Intel mainstream socket mounting holes. Heatsink mounting holes, and that might cause compatibility issues with certain, well, I can't see it being too much of an issue. The main concern I have is, if the IHS of a AMD CPU is higher than where the IHS of an Intel CPU normally stops, and you use Intel mounting hardware to mount a cooler to this motherboard, you're probably going to end up with, way more mounting pressure than you're supposed to have. Now, PGA sockets are very robust compared to LGA sockets, so that shouldn't be a concern, but I think there was a couple cases in the past where people had issues with, pin contact on AM4 and with certain coolers or water blocks. I can't remember right now, but yeah, so that's also potentially Asrock tried to make a very interesting motherboard here. I think they might have tried too hard to make an interesting motherboard and kind of overshot it a bit because, they could have maybe knocked down the V-core. They could have knocked down the V-core down to a 6-phase and then used a more normal VRM layout. And yeah, maybe then the thermals wouldn't be so great, but, that might have given them enough space to have maybe a better memory. I don't know if the memory section is bad. I assume it is, but if it is, then they could have, I would have sacrificed the VRM to get a better memory support, is what I'm basically trying to say. If that's the trade-off you have to make on a motherboard this size, sacrifice the VRM, get better memory support. Because most people will just want, they'll want their memory, right? They don't really care about overclocking Ryzen 3rd gens because they don't really overclock that great in the first place. And then the rear I/O is like, yeah, well, dongle, like, I don't think there was a good solution to that. It was like either Thunderbolt 3 or no Thunderbolt 3. And I assume that Asrock decided that, well, it's a kind of workstation-y class platform, so the Thunderbolt 3 port to a lot of people, I get, like, to some people might actually be like a really great reason to go for this board. So, yeah, that's the X570 Phantom Gaming ITX Thunderbolt 3 from Asrock. A very interesting ITX board, and definitely with a really solid V-Core VR, like really solid VRM on it. But overall, it's kind of like, somebody needs to test this thing, like properly test this thing. And I'm not going to be doing it because I have too many boards to test already. So, or at least if I'm going to be doing it, it's not going to be anytime soon. Let's put it that way. So, yeah, I kind of wish they would do like a more... Like, if they could keep the VRM, scrap the Thunderbolt 3, rearrange the board a bit, like made a toned down version of this motherboard, I'd be a fan. Be a big fan. Maybe use a daughter board for... No, that wouldn't work. Maybe use a daughter board for all of this stuff. Well, okay, no, the oscillator probably wouldn't work over a daughter board, but they could try daughter board some of the stuff down here. Because that's just a bunch of voltage regulators, isn't it? Yeah. That's a voltage regulator. That's another one. That looks like another one. That looks like another one. That looks like another one. They could have totally just stuck a daughter board down there, as far as I'm concerned. Yeah, stick all of the voltage regulators onto a daughter board. Move all of this stuff into this area. That fan header has to not be where it is. And it would probably... Like, it could potentially be like a much... Well, it would actually probably cost more to do that again. So, yeah. Anyway, so... That's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. Or you can go and buy a shirt or sticker or posters or whatever from Teespring. There's a link to that down in the description below as well. So yeah, that's it for the video. Thanks for watching, and goodbye.